statistical class, and I'm also welcoming you to the new month of November. Today, the focus will be on further topics in hypothesis testing. In the outline, I'm going to walk you through the equivalence between confidence interval and two-sided hypothesis test for mu. Before, I think in chapter 8, I walk you through the confidence interval. And right now in chapter 9, I've walked you through hypothesis testing. The question is, what is the equivalence? If I take a decision using an hypothesis testing, if I construct a confidence interval, am I also going to take the same decision? And that is what I wanted to see today. And I'm also going to walk you through possible errors in hypothesis testing. Okay? Whenever we conduct hypothesis, we make errors. Then I'm going to walk you through that. And finally, we'll walk you through limitations and common misinterpretations of hypothesis testing. But I think we may not be able to cover all these three today. Okay, but let's see how far we can go. Like I said, I want to have a review. Let me first have a review on hypothesis testing for population proportion and population mean. The other time, I walk you through statistical procedure for constructing hypothesis testing for both population mean and population proportion. The whole journey started from assumption all the way to formulation of hypothesis, to test statistic, to computation of p-value, and to taking conclusion. I think we did that, for both population mean and population proportion. We are aware of that. But what we want to see now, is there any equivalence between the two? I needed to pay attention. Let me also say this. I've already uploaded practice question for exam 2. Check the module. Start familiarizing yourself. This time around, I put both solution and the question, and I'm also going to give a clue, just like the way I did, or en route to midterm 1. I'm also going to do the same for midterm 2. Okay? Now, the study guide also going to release chapter 7, chapter 8, chapter 9, chapter 10. That is what the midterm 2 will cover. Okay, now let me come back to the equivalence right now, and I need you to pay attention. We want to look at the equivalence between the two. We want to look at a problem, right? We're going to construct confidence interval. We're also going to perform hypothesis testing. We now want to compare decision. We really want to see whether there's going to be an agreement. I need you to pay attention now. Okay, example 9.4. It is important for nutritional information on food packaging to be accurate. A random sample of n equal to 10 frozen dinners of a certain brand was selected from a production line. The mean calorie content for these dinners was 246.6 with a standard deviation of 10.803 calories. The data is approximately normal with no substantial outliers. I needed to pay attention. Assumptions underlying the use of hypothesis testing and confidence interval, of course, is that, you should, the distribution is either the distribution is normal, and if the distribution is not normal, you should be taking a large sample size. And not only that, the sample you're going to choose have to be random, and there shouldn't be a substantial outliers. Outlier, according to Benkamp in 1982, is a data point that is not consistent with the rest. And if that is present, it's actually going to affect your hypothesis, the validity of your hypothesis testing, and the confidence interval as well. So in this example, you have been told that there's no substantial outliers. Now, when you take a look at question A, the packaging for this dinner, okay, list the calorie content as 240 calories. Let me equal to true mean calorie content of the frozen dinner and test whether or not, okay, the information on the package is accurate at 0.05 level. Now, there's something I needed to pay attention to. Whether or not. That's a two-sided. I told you the other time, you're going to be the one that will figure out the sign, the inequality sign that you're going to have in the alternative. The inequality sign in the alternative could be less than or greater than or not equal. But right now, whether or not means two-sided. Okay? Now, they give you the confidence, the level of significance to be 0.05. How do I actually conduct hypothesis testing on this? I want to show you right now. Number one, you're going to start with the assumption. Now, assumption of random sample hold, because we were told here that a random sample was chosen. So assumption of random sample hold. Okay, assumption of randomness hold. Now, even though the sample size that we have in the question is very small, how do I know it's small? Because it's less than the threshold set by central limit theorem of sample at equal at least story. But they gave you an information here that the data from which the sample was chosen is normal. Now let me tell you this. When the population from which sample is chosen is normal, irrespective of the sample size, whether small or large, okay, assumptions of normality hold. But if the population you are choosing from is not normal, okay, if you actually want to guarantee normality assumption, you must be choosing a large sample. So right now, we're fine because you've been told in the question that we're working with normal population, irrespective of the sample size. That's no problem. Now, because of that, I'm going to say on the assumption side, we're fine. Now, the next step is formulation of hypothesis. I told you the other time. The HO that we call the null hypothesis will always attract equality sign. The alternative in this case is going to be not equal because I showed you the other time, they said whether or not. That's a two-sided test. The next on the line is actually going to be the test statistic. This is the way you should arrange it in exam. Test statistic. You're going to write your formula how? It's going to be a T equal to that. I'm going to plug in my sample mean. I plug in my hypothesized value. I plug in my standard deviation. I plug in my sample size. And of course, I got 1.93. 1.93 is my test statistic value. Let me tell you this in exam. There's a difference between test statistic and test statistic value. Test statistic is a formula. This is a test statistic. But the value now, test statistic value is 1.93. Now the next on the line is going to be getting the p-value. And I told you the other time, if you want to get a p-value, you need to take into consideration the nature of the alternative. Whenever you want to figure out your p-value, okay, then you will actually need to look at the inequality sign at the alternative. Now, if I look at the inequality sign right now, if I want to get a p-value, because I'm working with a two-sided test, then it means I want to find 2 multiplied by probability of T9 greater than 1.93. Where is the 9 coming from? The 9 is actually the degree of freedom. The degree of freedom is the sample size minus 1. Okay, the sample number here is 10. The degree of freedom is going to be 10 minus 1. That's going to be 9. Whenever you are conducting a t-test, you need degree of freedom. And that's why you have a T9 greater than 1.93. Now, how am I going to implement this in R? If I want to implement this in R, this is the code. Because I want to get a p-value. We normally get a p-value when you are conducting hypothesis testing. Okay? I'm actually going to use PT, p-value for PT. And that's why you see a PT, okay? The very first number is going to be the value, your test statistic value, 1.93. Follow, you're going to put a comma, followed by degree of freedom. The degree of freedom is going to be 9. Then lower equal to F. Lower equal to F. That F means false because that sign is greater than. And that was why we say we're not dealing with lower. The moment you get a PT of that, whatever you get, you multiply by 2. Okay, but let me tell you this. If you come back into the test statistic, if you have a negative, please pay attention. Pay attention. If you have a negative, you convert it to positive. If you have a positive, it's still going to remain positive. I just wanted to know that when you are working with two-sided tests. So right now, I have a 0.0, I have 0.086. Now, it is now the time to compare the p-value that I got with a level of significance. I told you the other time, the level of significance is the level of statistical error. I'm going to say that again. The level of significance is a level of statistical error you're always going to be given. If you are not given, then use a standard level of significance of 0.05. Okay, now when I compare this guy right now, my p-value right now is greater than the level of significance. When p-value is greater than level of significance, we're going to fail to reject H0. When p-value is less or equal to level of significance, we reject H0. But there's something I want to tell you. You know, here we say we fail, and when you fail to reject H0, you need to put the level of significance because we fail to reject H naught at a 0.05 level of significance. Whatever level of significance, you're actually going to indicate that. And let me tell you this. We don't say, please pay attention. We don't. When we say we fail to reject H naught, does not mean we accept H naught. If you use the word we accept H naught, you're going to be wrong. Does that make sense? Now let me tell you this. If in a court of law, the null hypothesis is going to assume that the accused is innocent, that H naught is H naught. HA's alternative is going to say is guilty. If they are not able to reject H naught, okay, which means they fail to reject H naught, means they do not find sufficient evidence to do so. That doesn't mean the person did not commit the offense. That's not what they mean. But what they are telling the world is they do not have a sufficient evidence, okay, to actually reject that. So we fail to reject does not let me just say, does not statistically means we accept H naught. So avoid the use of that. It's either we fail to reject or we reject. Does that make sense? Okay. Now, here we're going to make a conclusion. There's not enough evidence to conclude that the true meat content is significantly different from what the label says. When you take a look at this guy right now, what he's trying to say is that you are here. That's what he's trying to say. We fail to reject that. Okay? We fail to reject the hypothesized value of 240. That's what they're trying to say. Now, the same question now, we now want to use the idea of confidence interval. Please pay attention. Pay attention. You know, we've actually conducted hypothesis testing. Okay, we've taken a position, right? We now want to go into the same question. We want to construct a confidence interval. Then we're going to compare decision as well. Now, but for effective comparison, don't forget, if I want to construct a confidence interval, I need level of confidence, right, to be given. If I want to conduct hypothesis testing, I need level of significance. Now, if I want to know the level for effective comparison, because we're told in the hypothesis testing, we are assuming 5% level of significance. If I want to construct hypothesis testing, it's going to be 95% confidence level. Does that make sense? So if in hypothesis testing, if it is 1% level of significance, then in the confidence interval, it's going to be 99% confidence. Does that make sense? And that is the reason why that is the reason why I want to consider 95% confidence for mu. Now, if I want to construct a 95% confidence for mu, this is my formula. So the formula, okay? Now, all what I'm just going to do is to plug in, okay, the sample mean, the sample standard deviation, the sample size, but I need you to pay attention to something here. Pay attention to this guy. We want to get a t-score. When we were conducting hypothesis testing, we were getting a p-value. Okay, we use a pt. But right now, we actually want to construct a confidence interval. We don't need a pt. Then what do we need? We need a qt. Does that make sense? Now, when you take a look at that, you're going to be wondering, if I want to get a t-score, I need level of significance. I need the degree of freedom. Now, the degree of freedom, of course, is going to be 9. You have a sample size of 10. 10 minus 1 is going to be 9. Now, and don't also forget, if I have 95% confidence, the alpha is going to be 5%. And you know what? 5% is 0.05, right? Okay. So, but the code I want to use is actually has to do with alpha over 2. Okay. If you take a look at this guy now, okay, that was why I'm dividing alpha by 2. Alpha is 0.05. That will be 0.025. And that was why you have in the subscript T, you have a 0.025 and 9. And what is a command? Now, if I want to get that, it is this guy. Do you see right now? QT, alpha over 2, degree of freedom, lower dot T equal to false. And when you do that, that will give you 2.26. So 2.26 is actually what the code is going to give you. By the time you multiply by standard error, you're actually going to have 7.73, this margin of error. And after that, at the end of the day, by the time you subtract the margin of error from the mean and add to the mean, you're actually going to get, that is going to be the confidence interval. Now, I need you to pay attention. If you construct a confidence interval, okay, and if you go back to the hypothesis testing, we fail to reject that value to 40. Now, agreement is going to come if 240 should lie in the interval. Now, let us see now. Let's see whether 240 lies in the interval. That we just, oh my God, look at that. There is 240 in the interval. That's an agreement. Does that make sense? Okay. Now, let me tell you this. If we have rejected H0, okay? If we have rejected H0, if you construct a confidence interval, okay, the values of the HO will not be in the interval. Does that make sense? Go ahead. Okay, this is what happened. You know, in the hypothesis testing, we fail to reject H0. In the confidence interval, for there to be an agreement, the value of the null hypothesis must be in the interval. And right now, what is happening? It is in the interval, which strike an agreement. And you know what I mean? The interpretation is that there's an agreement between your observation and your theory. I told you the other time, a scientist observes nature and formulates a theory. Now, what that means, whenever you have an hypothesized value in the interval, that strike an agreement. And that was why I said here, I said something here. Give me 1 second. Take a look at this. What conclusion can you make about the packet claim based on the hypothesis test and the confidence interval? I said, notice that 240 calories is in the 95% confidence interval for mu. Therefore, we can use both hypothesis test and confidence interval to conclude that 240 calories is a plausible value for mu. Why? Because we fail to reject the non-hypothesis, okay, that the value is 240. And by the time we construct the confidence interval, we can see 240 lies in the interval. But let's say we have rejected, for instance, if you reject the non-hypothesis, by the time we construct the confidence interval, that value will not be in the interval. That's another agreement. Have I answered your question now? Okay. Oh, go ahead. Okay, go ahead. Yeah, the essence of doing the confidence interval is we want to see whether there's going to be an agreement. So if there's an agreement, then some scientists can decide to say, okay, I'm only going to conduct hypothesis testing. Some can say, okay, I'm only going to construct a confidence interval. But at the end of the day, they are taking the same decision. That's what we mean. Does that make sense? Okay. Now, and because of that, please pay attention to this. If I am testing the null hypothesis, or that the value of a parameter is assumed to be a particular value against alternative, okay, against alternative, okay, like I'm testing this guy against this guy. Don't forget, I have a two-sided test, right? Now, take a look at this statement here. If mu naught is in the interval, what happened? Then mu naught is compatible with the data. Then in that situation, we don't reject H naught. That was what we did. Now, another beautiful scenario, okay, if mu naught is not in the confidence interval you construct, then that means mu naught is not compatible with your data. That's a disagreement between your observation and the theory you formulate. In that situation, you reject H naught. Do you see that? So which means without you conducting an hypothesis testing, you can take a decision with confidence interval. That's what it means. So if I construct a confidence interval and I look at the value in the non-hypothesis, in the values in the HO, if the value is fall within the confidence, then I will fail to reject. If the value doesn't fall within confidence, then I will reject. What have I done? I did not even conduct hypothesis. I only constructed a confidence interval, which is an alternative way. Does that make sense to everyone? Okay. Now, confidence interval and one-sided test for mu are not compatible. What have we just done? Confidence interval and two-sided test. Now, when you're talking about one-sided test, we also have one-sided interval. We have not done that in this class, so I'm not going to talk about that. But I also want to tell you, if I have a one-sided hypothesis testing, we also have a one-sided confidence interval. Does that make sense? So what I'm trying to tell you now, okay, confidence interval is not the same as a one-sided test, but we have a one-sided confidence interval. Okay, now I just wanted to take note of that. But let me also tell you this. When you are focusing on proportions, okay, then the equivalent is not going to be there. That equivalent only work for mean. Does that make sense? That's what we mean. Now, I want to go into, I think today I'm going to spend my time on possible errors in hypothesis testing. On Monday, I'm going to continue on the misconceptions, the third objective. But I want to welcome you into possible errors in hypothesis testing. Now, let me tell you this. Whenever we're taking decision in a stochastic world, okay, I told you the other time, we live in a probabilistic space. Because of that, at times, our decisions will come with errors. In the court of law, let me tell you this, in the court of law, where they are deciding about whether to free this guy or to jail this guy. The judge, the defense counsel, and the prosecuting counsel, they were not at the crime scene. Imagine that. They were not at the crime scene, but they want to judge a case about whether this guy should go to jail or not. Now, there's possibility they could make errors. Does that make sense? And also in hypothesis testing, where we want to take a decision whether to reject or fail to reject, there's also possibility of making error. How do I know? Because George Box said, and I quote, all models are wrong, but some are useful. All models are wrong, some are useful. We're using model to depict reality, but model can never give us an exact characterization of reality. There's always going to be a gap. That's what we mean by error. Now, what are the possible errors in hypothesis? I need you to listen now. Let me tell you this. We find ourselves in a world where we want to speak the mind of nature. Why do we want to speak the mind of the nature? Nature knows the truth. At times, we can guess right the mind of the nature. At times, it may be the other way around. Now, take a look at this. Take a look. If nature have it that the H naught is true, if nature have it that H naught is true, if we do not reject H naught, then we've taken correct decision. Does that make sense? Nature have it that H naught is true. Oh, nature have it that this guy did not commit the offense, because in the court of law, the non-hypothesis is that this guy is innocent. Alternative is that he's guilty. And if the nature have it that he does not commit the offense and the court sets him free, then the court has taken correct decision. Take a look at another one. If the nature has it that alternative is true, if the nature have it that this guy commit the offense, okay, he really commit the offense, and the court rejects H naught, of course, HA is true, and they reject H naught, that's a correct decision as well. Does that make sense? But let me tell you this. The possible errors that we have in hypothesis, I'm going to start with type 1 error. If H naught is true, if nature have it that H naught is true, this guy did not commit the offense, okay, by nature, but we reject H naught. The judge will set this guy to jail, okay? Is that good? That's not good. That's a type 1 error. So the type 1 error is committed when H naught is true, but it is rejected. Okay. Another type of error is type 2 error. Okay. Take a look at this. HA is true. Okay. Okay. HA is true, but we do not reject. HA is true, but we do not reject HO. That is type 2 error. Okay. If you take a look at the type 2 error now, okay, the type 2 error is that this guy is guilty, but the court sets him free. Now, because of these two possible errors, every day, my wife and I, we spend a lot of time talking to our 5 lovely girls. The one in college, the one in high school, I was also doing a PSEO program, and the one in the middle and the elementary school. We sit them down, we let them be aware of the reason why they need to stay out of trouble. Because there's possibility those who did not commit the offense, they can be in jail. There's possibility those who commit the offense, they can be set free, which means criminal live around us. If you really want to know which one is more dangerous between type 1 and type 2, it depends on the context. But what I know, in the criminal justice system, they want to minimize. They believe type 1 error is more dangerous because they want to make sure innocent person did not go to jail. And somebody's going to argue this out. What about type 2 error? Can we say it's also more? Okay, criminal live around us, but we know one day it's still going to be caught. So that is more or less better than sending an innocent person to jail. Now, let me tell you this. I just give an example in the criminal justice system. I want to give an example in weather forecasting. Yesterday, we got a surprise snowfall in the state of Minnesota. Did you all see that, right? Oh, did you like it? Oh, my children, some of them like it. Snow, they were like, okay, now let me tell you this. Let's say school district. If they saw that ahead of time and they asked school children to stay at home, okay, believing that there's going to be a snowstorm, if eventually there is no snowstorm, that's a type 1 error. But in that situation, the student can sit at home, they can still have a class through Google Classroom, right? We want to say the one that is more dangerous. Let me now tell you type 2 error in that very context. Let's say they did not see snowstorm coming and they asked children to come to school. And eventually, that was a snowstorm. They are putting the life of the children and the bus driver at risk. That's a type 2 error. Which one is more dangerous in that regard? It's type 2 error. Does that make sense? So whether type 1 error is dangerous or type 2 error, it depends on the context. I'm going to give you another context because on Monday is when I'm going to go through example. I'm going to start on page 17, but I want to give you another example. I'm going to cite example of this in medical field and in national security. Pay attention. Do you know how I understand my statistics and mathematics? I understand them perfectly because I relate them to real life situation. I try to unravel everything behind the question, behind model, and so on like that. Now, let me give you an example in the medical field. In medical field, in medical diagnosis, there's something that we call false positive. Has anybody heard about false positive? False positive is type 1 error. I also have false negative. For instance, the false positive, this guy went for a COVID test. He went for a COVID test. And nature knows the truth. This guy doesn't have COVID. Nature knows the truth. But by the time they test this guy on the medical equipment said this guy has a disease. That's a type 1 error. And you know what is going to happen? This guy will be affected psychologically. Okay? That's a false positive. Now, let's look at type 2 error now. This guy has a disease. Okay, nature knows the truth. He has a disease. Nature have it that he has a disease. But by the time he go for test, okay, the machine said, no, there's no disease. What is going to happen? This guy is going to be walking freely as if nothing happened, but that is dangerous. That's a type 2 error. Does that make sense? Now I'm going to give you the last example now that I want to give is on national security. And you are going to be the one that will decide which of the type 1 and type 2 error is dangerous. Now, let me tell you this. If a particular country allege some individuals of terrorist or threat or attack, or they allege international foreign government, and nature knows the truth, if that foreign government or those individuals are not even planning any attack, do you know what is going to happen? Number one, the government will start deploying resources, wasting resources. The citizens, they're going to be panic. You understand what I mean? That's a type 1 error. And that will lead to what I call a strain in international relations. But look at type 2 error. On the other hand, there's a genuine terrorist attack, but that means the intelligence of a particular country. What do you think will happen? Okay, that will be catastrophic. Like that could be damaging, that may be the end of that country. That's a type 2 error. So in national security now, the one that is more dangerous is type 2 error. You can see I've given different kind of scenarios of how type 1 and type 2 error can be. Yeah. Okay, so let me give you a definition. Type 1 error means when HO is is correct and you reject it. That's type 1 error. HO, the non-hypothesis, is right, but you reject it. Type 2 error, the non-hypothesis is false, but you fail to reject it. Do you see the difference? Type 1 error is rejecting the non-hypothesis when it is true. Okay? Why type 2 error is failure to reject the non-hypothesis when it is false. The non-hypothesis is false, but you fail to reject it. Does that make sense? I think I've given you different kinds of scenario, but you know what I'm gonna do next here. I'm now gonna walk you through. Let me see my time. I think I still have like 3 minutes. Oh, let me stop here. I'm gonna start from here. I think I have 4 more slides. I'm gonna add this to my next lecture. Like I said the other time, before you go, before you go, before you go, exam 2. We are counting down to exam 2. I've already released exam 2 practice question with solution. I need you to get yourself familiarized with that. And next week, I'm actually going to bring your midterm 1 booklet to the class to be given to you so that you're going to look at it. You're going to see, for those of you who score less than 100, you're going to see what you miss. And I'm also going to release midterm 1 solution. Does that make sense? Make sure you all stay safe. Have a lovely weekend. Bye for now, everyone. I'm recording. I'm recording.
I have a question. You said at your example here that when there is a genuine, like the thing happened, okay, it's a type 2 error because they failed to intercept.
Yeah, so type 2 error, yeah, the type 2 error is like you are rejecting, or what, you fail to reject the non-hypothesis when it is true. So in the case of the national security, type 2 error is there's a genuine threat, but they miss
failed
that.
to intercept.
Exactly.
And type 1 error,
There's no genuine threat
but
like a
they
false
took.
alarm. You know what they call
Okay.
false alarm?
Oh, okay.
Yeah. Does that make sense?
Yeah.
That's why I call false positive. Type 1 error is false positive. Type 2 error is false negative.
Okay.
Yeah.
Yeah. Thank you.
You're welcome. Yep. That two things mean proportion, for p-value, p norm. Testing for me, for p-value, et. You're welcome. Yeah. I mean, very- yeah. What I'm gonna do, I'm gonna um, if you have an extra, so when I'm gonna
Yeah.
weekend.